Welcome to lecture 47 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. Myself Mukul Kumar Das from Department of Electronics Engineering, IIT ISM Dhanbad. Dr. Syed Sadiq Anwar Askari is currently faculty in Manipal University, and Mr. Pranav Kumar, Senior Research Fellow at IIT ISM Dhanbad. They are assisting me in conducting this course. In this lecture, we will focus on simulation of thin film solar cell using SCAPS-1D. In last lecture, we have discussed how to install SCAPS and the basic features of the working environment of SCAPS-1D through some snapshots of different steps of a SCAPS programming. In this lecture, we will continue the simulation of thin film solar cells using SCAPS-1D. Getting started. So first you have to define the problem. So this is the first action panel as I discussed in last class. This window you can see after opening this. Here in the box you can find there is a set problem. This set problem basically it defines the problem, the geometry, that is the structure, the materials and all properties of your solar cell structure that can be controlled by the set problem. So whenever you click on the set problem, it will be like this. So there is layers. Already a program is developed. That's why after opening this, you are getting these layers. Already this left contact, P plus silicon BSF, P silicon bulk. P silicon bulk is there. P silicon BSF, P silicon bulk already. But if you start with a new problem, in that case, whenever you will be adding layer, this add layer button is there. So it will start from that. So when there is no layer, nothing will be showing in the picture here in this window, and only you have to start from the first layer, add layer. But here already some layers are added, but it is just to show how you can control this. So this basically this window, it is setting layer and contact properties by these things. And if you like to set the interface properties, so here interfaces properties are also there. So side by side there is a layers, another is interface window. You can see all these things. And click on add layer. So first suppose left back contact, this is a back side, then add layer button, because already if there is no layer, you have to add layer. So first add layer, if you click this, so new layer properties then will be coming. So click on add layer button. When you click the add layer button, you see there will be coming this layer 1. Here you can say, you can write the name of this layer. So you see the parameters which is coming after clicking the add layer button. Thickness, this is in micron. You can set other values also. Say 2.000, you can change the value here. The layer is pure, that is this uniform. Semiconductor property of a pure material, I will be coming one by one this parameter. Band gap value, electron affinity, permittivity value, conduction band effective density of states, valence band effective density of states, electron thermal velocity, all the associated values, whatever we have discussed in our previous lectures, different lectures of modeling, almost all the values are there. If you like to allow tunneling, then you have to click this box if there is a tunneling. And if you click the box, obviously you have to put the value of effective masses, because tunneling depends on effective mass. No ND grading, there is a uniform, if there is a uniform doping concentration or there is a gradient in the doping concentration, that can be also controlled by this. Some recombination models also window will be opening after at the time of add layer. So let us see one by one the parameters of this. Layer name, say layer 1. Each layer represents a different materials in the cell structure. Here we are saying layer 1. This is the window of last slide. It is in a zoomed out way. So thickness can be represented in nanometer, micrometer, millimeter, centimeter, etc. And you have to specify the physical thickness by clicking the unit. After clicking the unit, you can choose the value. Here it is coming. Whenever you click this, automatically this unit will be coming here. It is micron is clicked here, so this micron is coming here. And this is 2.0000. That value you can edit this value. Next is this layer purity. This indicates layer's impurity profile, and whether layer is pure semiconductor or intrinsic or not. In the material, that is uniform or graded, or from the file, that is you take the value from the file. If you like to have a particular doping profile that is mentioned in a file, that can also be incorporated here. And uniform pure, that is y is equal to 0. Uniform pure A, you see y is equal to 0. Uniform pure, this B, y is equal to 1. So different categories are there. So graded, this linear, maybe graded parabolic, etc. So you have to mention here, say by clicking any of this, and that will be reflected here. The layer is pure A, and this y is equal to 0 and uniform. And the uniform doping concentration also you can choose. And semiconductor property P of the pure material, that is you have to coming here. And next you can choose the band gap values. So doping also you can, purity of the layer you can mention, and then is the band gap. Band gap is electron volt, in electron volt, that is 1.2 for say silicon, or 1.12. Electron affinity, editable value. Dielectric permittivity is editable value. Effective density of states in the conduction band, that is NC, editable value. Per centimeter cube, this unit is there. Valence band effective density of states, also this 10 to the power 19. In this value you can edit this value. Electron thermal velocity, VTH, which will be required to calculate the lifetime along with the capture cross section. Whole thermal velocity, electron mobility, whole mobility, all these values of a single parameter, single layer. And if you mention tunneling, as I already mentioned, tunneling will be there. I will come later for the tunneling. So these are the layer properties, the layer thickness you can mention. Now, so these are the materials, all are summarized in the left side. Already I discussed, these are the values you have to give. Now the doping parameters, that is very important. Is for uniform doping, whether the layer is near doping or not. In the last slide, if you remember, different type of grading is there. So you see, this is the function. No ND grading. No ND grading means uniform. There is no grading of donor concentration. Shallow uniform donor density, that value, and no NA grading, acceptor grading. So shallow uniform acceptor density you can mention. So let us go to that slide now. Here you see no ND grading, there is uniform, that you have chosen. No ND grading, uniform, this value. Here also this value, and shallow uniform donor density, that value is mentioned. So this for uniform doping, no ND grading option you have to choose, that is uniform. And ND, that is a donor concentration. If it is a grading dependent, there is one position of X. Suppose generally in a PN junction, there is a abrupt PN junction is not available. Sometimes the doping concentration gradually changes from the one position to another position. Not abruptly it reduces to 0. That means suppose you are considering a PN junction, ideally we are considering that doping concentration looks like this. Suppose this is the PN junction. For a abrupt p-n junction, it looks like this. P, N, and if you plot the doping, it looks like this. Say Na concentration should follow up to this value and suddenly it should goes to 0. This is the ideal case. This is the Na profile. Similarly, Nd, it looks like this. Nd. This is the ideal case. Abrupt junction. But actually what happened, you see in actual value, it looks like this. This value changes in this way, is Na value, and Nd value so this is a grading with position. This is a position. So position. So grading is there. That grading profile also you can set in SCAPS. And donut density also in per centimeter cube you can mention, and that is uniform, linear, whatever the value you can have. So in this way, doping concentration of the layer also you can control. Absorption interpolation model. So this is absorption interpolation model. This is alpha. There is another property of layer material, that is absorption. It was mentioned here. If you see the basic window, here it is actually under this condition, it is there. So this is specific illumination and this is model, illumination model, etc. So absorption is coming after this. Yes, you see here. So just below the parameters, there is an absorption interpolation model. This appears. So this list of absorption submodels present in the SCAP. So how can you control this absorption model? The alpha is for material A. Actually, you can set the value from a file. If you like to from file, you have to mention the path of the file name along with the path, and the set absorption model also you can say. Suppose you have a list of absorption coefficient as a function of wavelength, say as a table format, lambda say 1 this absorption coefficient, lambda 2 this absorption coefficient. In this way, in an array format you have a file stored, so that value of alpha can be also incorporated here. And the optical absorption coefficient, that is alpha. So this alpha can be stored as a ASCII files, that is a simple text files with extension .abs. You have to save the file at a .abs, and in the file you have to plain text, you have to mention absorption coefficient and as a function of lambda wavelength. And here you see this path is given. Already in the library this absorption file is there. So from the file you are taking, so this C drive program files, these are the folders. Absorption, under absorption there is a silicon.abs. This file is already stored. It can take from here and it can calculate. You can generate a new file also. There is a custom absorption file that can also be mentioned here to get these things. But here, anyway, under this absorption folder you have to create that file. Recombination model, there is another window corresponding to the recombination model. It is appearing in the front side like this, in this way here. You see, just in the layer, under layer there is a layer property, layer material parameters, then absorption model, and in the right side there will be recombination model appearing. This recombination model, here you can mention the different types of recombinations. Say radiative recombination, and then coefficient is there, Auger recombination is there, Auger hole capture, Auger electron capture, in that case both you can say. Recombination at defects, and defect basically Sockler-Edel recombination, that is recombination, and another is band-to-band recombination also present. But if you mention the recombination at defects, that means you have to mention the defects also. So defect, the add defect, this button will be there. So up to 7 defects can be introduced in a semiconductor layer, a particular layer. 7 type of defects you can mention. The parameters governing each defect can be edited by clicking the appropriate edit or add button. So edit defect 1, add defect 2. There is already one defect already added. So this is edit. So you can edit the defect. To add the new defect, add a defect, that will be defect 2. And defect 1, detail about the defect 1, in the edit button it is coming, say defect 1. Charge type neutral. So acceptor kind of defect may be there. There may be donut type defect. Total density, that is, what is the defect density? So that also uniform or not, it is. Grading, if is not there, then uniform. Energy distribution, that is also very important. Generally we consider for simple analysis that the at the middle the single trap level, and for single trap level, you suppose this is a conduction band minima and this is a valence band maxima, and this is the trap level, single value trap level, ET, suppose. This is EC, this is EV, and this single value and the position of that single value for trap level, that also you can mention. Here you mention that single, it is mentioned single here. Energy distribution, this is single. ET is equal to 0.6 electron volt above EV. Valence band is 0.6 electron volt above the valence band maxima. So tau n, tau p automatically calculated. If active, then ln and LP. So if tau n is there, tau p is obviously will be defect based calculation, and automatically the diffusion length will be also calculated. So another type of defect you can add. So there may be a bulk defect, there may be an interface defect, there may be a surface defect. So you can add a different types of defects. Here it is shown in detail, say defect 1 of P layer. So defect type, neutral, capture cross section, this window, already I discussed in last slide. So this is a zoom out version of that. In this way you can define or you can edit the properties of defects. Now suppose these layers are already made by this, and now the illumination property. Illumination property is generally appearing here. Illumination, you like to analyze the performance under dark condition, that you can do. Under illumination condition, that also you can do. Illuminated from left or illuminated from right, all things will be there. So right and left, you can flip, you can change the switch. Illumination from the left side or illumination from the right side. And generally, the structure in these SCAPS are in the lateral way. So not the top and bottom concept. There is a concept of left and right. Here you see in the particular example, so this light is coming here and different colors, arrows are indicating the different wavelength of light. So almost all wavelengths of lights are coming. That's why it is different colors it is shown. And from the right side it is illuminated. You see, illuminated from right button. Right, this one is enabled. This one is the right one is enabled. This is from right. So that's why it is coming. If you choose left, automatically it will change. And also apply voltage. Here you can see apply voltage V to the structure from left contact or right contact. Here also this is selected from the left contact, voltage V to left contact. You see in the left contact this V is applied here, this V, this value in the left contact. Here also it is left contact is given. So the voltage can be applied here, and this voltage V02 is a current reference as a consumer and generator. So that terminal will consume the current or will generate the current. Invert the structure. Simple one button option is there to invert the structure. Just it changes the right side to left side and left to right side. So there is option of also inverting the structure. And automatically the right contact, this is the front side, it is grounded. Whenever you put the value on the left V, automatically the other contact will be grounded. Here you see the right contact front, it is mentioned that this is a front contact, the right contact is the right side contact is front, this is reflected here. So from this light is coming. Another is numerical settings, I will be coming. So illumination setting, voltage setting also can be done after adding all the layers. Here actually you can verify this is a left contact, there is a back, you have mentioned this is a left contact as a back, right contact as a front. This is the layers, this is the layer description in this is a layer description here. Left contact is back, it is named as left contact back. P layer, then this is a P layer, is a red color. N layer, this is a blue color. Then add layer means you can add further layer but no other layers are added, that's why this is ended here. And then in the right contact in the bottom, at the bottom. So if you add layers, so other layers will be appearing here and figure also will be changing here. Then you right contact and right contact is there, and then illumination setting you mentioned from which direction light to be given, and then automatically the structure will be generated in this window. Now working conditions you have to define. After generation of the structure or the solar cell structure or any geometry, working condition you have to mention. So this is again the action panel. Here in the top left there is a working point. Temperature 300 generally, there is a room temperature. Voltage is 00. Frequency says 1 megahertz, it is given 10 to the power 6 is hertz. Number of points, all these things are there, and the working point specifies the parameters which are not varied in a measurement simulation and which are relevant to that measurement. So these, whatever you specify, this will be remaining constant for a particular measurement. Let us see how these are working. Illumination, say light condition, dark light. Yeah, under illumination it is details shown. Under light condition there is a internal SCAPS calculation of generation GX. Under this there is a from analytical model for spectrum. External spectrum file both can be given. If you under light, this can be also mentioned here under illuminated condition. Then you have option, you will be giving specify illumination spectrum, then calculate GX. This option will be there. Directly specify GX, you can do direct, you can also specify directly, but here it is selected. This selected means this one is selected. That means illumination spectrum, then calculate GX. Illumination spectrum you can set either from any model for the spectrum or some external spectrum file, the stored file. And if it is dark, there is nothing from the thing. And if you directly put the directly specify GX, that is this option, if you click the directly specify GX value, this if you would click here, if you would select there, it would be coming again two forms, that is from analytical model and external file to read generation GX. So you can directly put the GX value, sometimes it is required. Instead of giving the model for the spectrum means from the spectrum it automatically calculates generation rate by alpha, that formula that you remember, there is alpha into front surface reflectivity 1 minus r, if r alpha 1 minus r e to the power minus alpha x, and phi intensity I, alpha I e to the power minus alpha x intensity, that it can calculate. But after calculation from any another program, you can directly specify the generation rate also. So under illumination, these are the option, and specify illumination spectrum. Here also AM say 1.5. You see, these are the files you have to mention. AM 1.5. If you select the spectrum file, it will come from here. Here it is specify illumination spectrum, then calculate GS. It is selected, and under this select spectrum file is selected. That's why these program files under this path, this is the directory. Then under spectrum AM 1.5 1 sun dot spectrum, 1 sun 2 sun etc. different spectrum may be there. If you choose the file here, this file from automatically you take this the spectrum that is irradiance value, that is intensity value will be taken, and sun or lamp also it can be taken, incident or bias light power. Light power is watt per meter square, that is the 1000 watt per meter square for AM 1.5. that will be required to calculate efficiency, because in the denominator part, if you remember the formula as a in the denominator of the efficiency formula, power conversion efficiency formula, there is a input incident light power, and from this spectrum the calculate generation rate, so it will calculate generation rate. Otherwise you constant generation rate, there is option to use the constant generation rate also, you can select. Without giving spectrum, you can directly give the generation also. If you give the spectrum, no need to give the generation rate, and if you like to give the generation rate, no need to give the spectrum. So these all are summarized here. Select spectrum file is accurately calculate. Illuminated side right or left, that also you can define, that I have already shown. Fraction of light transmitted after ND filter, that is also there. So this transmission percentage you can set. Lamp power, this usually set 1000 watt per meter square for one sun standard, because you just imagine there is a suppose solar spectrum like this. Is a suppose wavelength. At every wavelength from this spectrum file, whatever you are mentioning, you can calculate the irradiance value, all these points, and to calculate the current corresponding to a particular lambda, you have to select a values at different lambdas, that is different wavelengths. That is irradiance, suppose irradiance. Total J lambda you have to first calculate at a particular lambda, then you have to integrate over lambda minimum to lambda maximum range d lambda to get the total current. Okay, but in case of formula in the power conversion efficiency, there is a Vm into Im by P incident. This P incident is the optical power, and this volt into ampere. Volt into ampere means volt into coulomb is energy, and coulomb per time is the current. So volt into ampere, this gives you also watt. There is a rate of, that is change of energy, rate of energy, that is joule per second or watt. So this watt is electrical wattage you are generating, and this is input wattage applied. In this case, this will be taken as a 1000 watt per meter square, and this per meter square, so better to calculate, this is Jm by A area, if you put this area per incident into area. So 1000 value of this P incident will be the 1000 watt per meter square. That is nothing but total area under the curve. That indicates the total power incident. So from the spectrum file, it can calculate the individual J lambda, but the total power, optical incident power, it should be area under this curve. From that you can calculate, and that will be 1000 generally you can specify the total power. Now, this illumination model, all these things, custom generation profile, GX, if it is mentioned, then GX model, constant generation, and other model also you can, analytical model you can choose for custom generation profile, you can edit, you can import. Particularly, this is important when simulating the textured surfaces, nanostructures, or multi-layer optics, because this SCAPS does not have optical model to calculate the actual generation due to scattering of light, due to multiple reflections, etc. Rather, another optical models are available that can accurately calculate the profile of light, that is intensity. From that you can calculate the generation profile, and that generation profile can be directly incorporated in this SCAP for electrical simulation. So that's why a custom declared or custom generation profile is important, and that option is also there. You can do this. And this model basically generates a position dependent generation rate. So generation profile we have discussed if we in optical modeling. Now select a GX file. If you have a generation profile, that can also you can store, and you can call this file from the select GX file option. Transmission of attenuation filter. So fraction of light transmitted after optical attenuation filter, that also can be mentioned here. You see the transmission of attenuation filter, percentage of transmission you can set. Ideal light current in cell, that is different parameter. We'll discuss later. Now series and shunt resistance, these are two also important parameters which are very important for accurate modeling of the solar cell. So this series resistance and shunt resistance window looks like this. It will be also appearing in the main work environment of the SCAP. Here you see the series resistance, yes is clicked, and you have to mention the value here, ohm centimeter square in this, or Siemens per centimeter square. And shunt resistance, if it is yes, that means again you have an option to put the value, and generally shunt resistance is very high, ideally it is infinity, so that's why it is given very high, you can mention here. So this series resistance is offered by the bulk of the observer layer, etc. So this can be implemented by using this. Shunt resistance, you see this is the value ohm centimeter square, as I mentioned. Either you can mention the ohm centimeter square or Siemens per centimeter square in this way, and this is RSH, or you can say GSH also, 1 by RSH. There is a conductance also. Alternatively, the way to define the shunt resistance is of conductance, GSH. There is Siemens per centimeter square. This will be ohm centimeter square shunt resistance or Siemens per centimeter square. But this value, this RS value, series resistance, there is a option of only values. You can put the value in ohm. In unit is ohm centimeter square. Sorry, this series resistance is ohm centimeter square. But in case of RSH only, Siemens per centimeter square is valid, because alternatively use this. Either you mention here or you mention here. Both is not required, because both will be contradictory. Suppose you are putting RS, then GSH should not be given, or you can put GSH and RS should not be given. Now you have to mention what type of measurement you like to do, say IV measurement or CB measurement, whatever things. So for that you go to again the action panel total window is looking like this. Here you see this is action 1 window is marked with the red. This type of action will be coming. Here IV, CB, CF, EQE, that is quantum efficiency, all values are there. If it is IV, correspondingly V1 volt, V2 volt, stop after VOC, what voltage, or how many points, what is the incremental voltage, all you can set. Say suppose, say you want to plot the graph for V0 to say 3 volt. So 0 volt, put here the final voltage 3 volt, and then these 401 points, how many points, that means that is increment, either increment you mention or you can increment the points. So similar thing. So in this way it's a 0.002, that is so many values, it is more accurate or more fine calculation will be there. Similarly CB, you have to mention the voltage. Say here it is mentioned minus 0.8 to plus 0.8 volt, and there is a 81 points, 0.02 increment. So all these increments and these things you can mention here. So whatever the actions you like to mention out of these 4 is IV, CV, CF and QE. These 4 are the measurement options for in the SCAP. You can measure. Now one by one IV, already I mentioned, this is the IV steps. You see these are the values V. IV, CV simulation voltage range has been given, and this voltage range also mention increment values, other things. Now for the CF and QE, quantum efficiency measurement, that's for CF measurement, the frequency, starting frequency, ending frequency. Say this is 1.00 u to the power 2, that is 100, this is 100 Hertz, 0.1 kilohertz to 1 megahertz. This is a Hertz, there is a Hertz is the unit. So 10 to the power 2 means 100 Hertz to 1 megahertz. Points, number of points, and the points per decade, that is important, not increment. Here points per decade. Per decade means actually the frequency is plotted in logarithm scale, otherwise you cannot accommodate all these huge range in a particular scale. That's why this is in logarithm scale, and points, how many points per decade means per 10 increment. So say 10, then 10 to the power 1, then 10 to the power 2, 10 to the power 3. So from how many points you like to have between 10 to the power 1 and 10 to the power 2, or between 10 to the power 2 and 10 to the power 3, this range, that is the points per decade. And quantum efficiency, there is a value you have to mention, that is wavelength 1, WL means wavelength 1, which wavelength to which wavelength, because quantum efficiency, the spectral response also, you know, related to the wavelength specific. So for a particular wavelength, internal power conversion efficiency, sometimes it is called also, IPCE. The wavelength range also you have to specify, and each wavelength it will calculate and it will show you. And the points also, and the increment nanometer in the steps. So suppose 300 nanometer to 900 nanometer, but what is the incremental steps? 10. So 300, 310, 320, in this way it will give the result. This already I discussed. Now you have to run the program and specify the action to be measured. So calculate, after the set problem, you just calculate single shot or calculate batch or otherwise. You calculate our single shot. If you just click the calculate single shot, then it will come. The energy bands panel opens and the calculation starts in a single shot, and it will be looking like this. Band diagram will be there. First it will calculate the equilibrium band diagram. Here the conduction band, valence band, Fermi level in p side and n side, all are shown in different colors. And from this result you have to analyze the result. You have to do the analysis. What type of results are there or how it is coming. Here you see this is a EFP, this is a red color, this is a Fermi level here, this is a ECEV, this is a black color, this is a EC conduction band, this is a valence band, and also EFN, the inside. So this you see this is this Fermi level is closer to the conduction band. So this is the n side, and this is Fermi level closer to the, in this side if you observe, the Fermi level is closer to the valence band. So this is a p type. So although there are two different Fermi levels are shown here, but in generally in equilibrium value, what we used to do in our analytical modeling, we used to show the Fermi levels by a single dotted line. But here, in this way it is showing. Carrier density also, you see, is the holes in the red marks. In the left side, you see, this is a P, and then it decreases here. There is a almost sharp, but not sharp, there is a gradient is there. If it would be sharp doping concentration, then it would be very sharp like this. It would be like this, sharp decrement. But there is a gradient. And also the electrons, here it is low and it increases here. And total charge is calculated in the black color. So this is a total amount of charge. This is a modulus of these two charges, sum of modulus of these two charges. So just simple addition, this plus this, red plus blue, red plus blue, red plus blue. In this way, it looks like this. So depending on the doping, whatever you are mentioning in the layer properties, accordingly the doping profile will be observed here. Current density. This current density due to holes is a red color. Current density due to electrons are there in the total. And this is the total current. You see this is very less, minus 4 e to the power 1, minus 40, yes, minus side. This is milliampere per centimeter square. This is a, not less, this is a minus side. This is a 4, minus 4 into 10 to the power 1. That is minus 40, minus 40. So this is basically current, total current under solar cell, illumination, under illuminated. So ISC can be taken as this, 40 milliampere per centimeter square. The unit is also specified here. The occupation probability, that is defect states. If you mention the defects, also it will be showing. Otherwise the density of states will be like that in the bulk density of states. Always you, whenever the result you will be getting, you try to compare with the theoretical analysis whatever we have done in this course. Say density of states for bulk, you know, remember this for in parabolic this type of band, density of states we have obtained. So try to compare always the result whatever you are obtaining with the result of this theoretical result, then it will be more clear to you. Fermi levels and whole, or all the values, Fermi level, all the energy levels you can calculate and you can see after single shot. Already I have mentioned this is a position dependent energy band diagram. This is position dependent electron and hole carrier density. This is the current density. This is density of states. Now you can switch to one of the specialized output panels. Here, say generation recombination panel, IV panel, CB panel, CF panel, QE panel. So here we are at present, suppose these two panel are open. So you can switch from this, you can switch to one of the specialized output panels from this pattern. It is coming in the after run. And other important matter is how to export the data. Suppose you have to report, you have to generate some report based on your simulation. So in that case, the curve information, you see this is the curve information. And this curve information, you either export or save the results. Either exporting or by saving results, you can have a particular format of data that can be again plotted in Origin or in Excel to get the data. So if you save in this way and then you plot, you can have the data in a, as per your desired choice, or you can plot also. Here actually two curves. This is under no light condition and under light condition is a last curve. This is light condition. Under light and under dark condition, both curve. Here we are getting the I versus V. This is a quite natural. It is coming. you can observe the result of the recombination. You see this recombination currents, it is also shown, but different types of recombinations are there. Is a total recombination, total SRH recombination, total radiative, total OJ recombination, all types of recombinations are there along with the total recombination of all you can select or you can calculate. And the generation also, generation is the generally is a cyan color, this is a sky blue color, just like this, and this total recombination in this way it is shown. What is the color combinations? So detailed analysis of recombination, all these things will be done through an example, but you just see the all the different colors here. It is also mentioned here accordingly. So at left contact minority carrier in, so left contact this recombination, at the left contact there is at the contact there is a recombination. You know, at right contact this is also minority carrier P. Right contact is blue color. This curve you see, this is the curve. Because in the right contact basically holes are recombined, and in the left contact electrons are recombined. That's why this is a huge value and gradually it decreases. And at the interface, this color no interface recombination was there, that's why it is not showing. And total generation also, as uniform generation is almost showing. If you would use the generation profile of different types, it would be showing here. So this is position dependent generation profile. So as a initial setup, and for the beginners, how to start with the SCAPS and how to simulate one program on a PN junction under light or under dark, we have discussed. And I would suggest you to go through the programs, try to develop and then simulate, and again you go through the video and these lectures, then it will be clear to you and you will be able to simulate and you will be able to get the result. Band diagram first you have to observe after running a single shot, because understanding band diagram is very important. After that you go for different measurements. So these are the basic references for details of SCAPS, along with the books by Newman, where you can get the semiconductor physics and other physical models, say density of states, band diagram. So parallelly you try to compare the theoretical result and experimental or simulated results. Thank you.